everyone, welcome to this lecture. Plan for this lecture is as follows. In this lecture we will see some basic properties regarding polynomials over fields, and we will also discuss about Lagrange interpolation. The reason we want to discuss these concepts is that looking ahead this will be useful when we want to design an efficient threshold secret sharing scheme for any given threshold t which is less than n. So, what are polynomials over a field? So, imagine you are given a field with an abstract plus operation and an abstract multiplication operation. So, the polynomials over a field are very similar to usual polynomials that we are aware of, where we have integer coefficients or coefficients which are real number. So, if I say that I have a polynomial whose degree is t, and if the polynomial is over the field f, then basically I am talking about polynomial f of x which has t plus 1 coefficients. So, those coefficients a naught, a 1, a t, they are elements over the fields, and a 1 will be the coefficient of x to the power 1, a 2 will be the coefficient of x to the power 2, and a sub t will be the coefficient of x power t. So, in total you have t plus 1 coefficients, okay, and that is why this will be called a t degree polynomial, and all these coefficients are elements of field. So, it could be the case that all your coefficients are the 0 element, that is quite possible, but still we will call such a polynomial as a t degree polynomial. Or it could be the case that only a naught is say a t, the coefficient a sub t is 0, but remaining other coefficients are non-zero elements, right. So, all such polynomials will be called as t degree polynomials, right. And here the plus and the dot operation that we have in the definition of this f of x are not the integer addition and integer multiplication, but rather they are the field plus and the field multiplication operation. So, let us see an example here. So, imagine I consider my field f to be the set Z7 which has the elements 0, 1, 2, 3, 4, 5 and 6, and my plus operation in this field is the addition modulo 7, and my multiplication operation here is the multiplication modulo 7. Okay. So, this will be an example of a polynomial over the field Z7 which is a 4 degree polynomial. Okay. Even though it does not have coefficients for, or it does not have terms like x square and x cube, I can implicitly assume that it has terms like 0 times x square and 0 times x cube to be implicitly present in this polynomial f of x, right. So, this is an example of a polynomial over the field Z7, and here the plus operation and the dot operations. The dot operations are here, are the integer are the addition modulo 7 operation and the multiplication modulo 7 operation. So, let us evaluate or compute the value of this polynomial at say x equal to 1. So, if I want to compute the value of the polynomial at x equal to 1, I substitute x equal to 1 everywhere, but remember all the addition and multiplication operations are performed modulo 7. So, f of 1 will be 11 modulo 7. So, f of 1 will not be 11 because the plus and the multiplication operations are performed modulo 7. If I want to compute f of 8, then there are two ways to compute that. I could compute 6 plus 2 times 8 plus 3 times 8 to the power 4, and then everything I can reduce modulo 7, but that will require me to perform a little bit large computations, instead what I can do is the following. The element 8 can be reduced modulo 7 itself, because the element A is actually not a member of the field Z 7, but I can make it a member of Z 7 by reducing it modulo 7, because my operations here are performed modulo 7. So, f of 8 will be the same value as f of 1, and we have already calculated f of 1. So, you can verify that does not matter whether you compute f of 1 and then equate it with f of 8, that will give you the same result, or if you directly plug in the value of x to be 8 everywhere and then compute everything and then do modulo 7, you will get the same result. Okay. So, that is an example of a field and polynomial over a field. You can have any abstract field with an abstract plus and abstract dot operation, and then you can define polynomials. Next, we define what we call as root of a polynomial, and this is again similar to root of an equation that we are familiar with in the integer world, right. So, if we are given an equation, say x square plus 2x plus say, or an arbitrary equation x square plus ax plus b, then we say that c is a root of this equation if I substitute x equal to c and get 0. So, I carry over this definition for polynomials over field. So, imagine f of x is a polynomial over a field in the variable x, then a value v from the field or an element f v from the field will be called as the root of this polynomial if the polynomial evaluated at x equal to v gives you the 0 element of the field. Again, this is not the numeric 0, this is the 0 element of your field. So, again let us take the example of the polynomial that we have defined that we have written down above, where my field is Z 7, and now it is easy to see that this polynomial has no root, because f of 0 is not 0, f of 1 is not 0, f of 2 is not 0, f of 3 is not 0, and like that f of 6 is also not 0. Now, you might be wondering why can't I say why I am only restricting to x equal to 0 up to x equal to 6. It could be possible that there is some value greater than 6 such that f of x takes the value 0 for this particular f. Well, that is not possible, because if you take any x greater than 6 and try to compute the value of f of x for such an x, then that will be one of these 7 possible values. It will be either f of 0 or f of 1 or f of 6, because f of x will be same as f of x modulo 6 x modulo 7, sorry, right, and this will be either f of 0 or f of 1 or f of 6, but all these 7 values, none of them is equal to 0, and hence it does not matter whether your x is greater than 6. Also, if you evaluate f of x for such an x, it will give you a non-zero value. So, that shows that this polynomial does not have any root. Okay. Whereas, if I consider another polynomial g of x over the same field and compute the value of g of 0, g of 1, g of 2, g of 3, all of them turn out to be 0. That means, this polynomial has 4 roots. Now, you might be wondering, is it possible that this polynomial have more than 4 roots? Well, we have a general result which is similar to the results regarding the number of roots that you may have for an integer polynomial. By integer polynomial, I mean where you have the integer coefficients and the plus and the multiplication of the integer plus and the integer multiplication. So, this result is regarding the number of roots that you may have for a polynomial over a field, and the result says that if you take a t degree polynomial over the field, then it can have at most t roots. That means, either it can have 0 number of roots, or it can have 1 root, or it could have 2 roots, or maximum it can have t roots. Now, it may be the case that some of them are all of them are distinct, some are repeated. you may have different possible cases, but in total the number of roots that you may have for a t degree polynomial over a field is upper bounded by t. That is the maximum number of roots you can have. Okay. So, I will not be going into the proof of that theorem, that is not required, but we can prove it. If you are interested, you can refer to any standard text in abstract algebra. Another interesting result regarding polynomials over the field which we will be using is the following. If I consider two different t degree polynomials, and when I say different t degree polynomials, by that I mean there is at least one power of x for which the corresponding coefficients are different in the two polynomials. It is not the case that all the coefficients of both the polynomials are identical, because if that is the case, then basically they are the same polynomial. When I am saying that they are different polynomials, at least one of the coefficients or one of the power of x will have different coefficients in the two polynomials. So, the result says that if you take two different t degree polynomials over the field, then they can have at most t common values. You can't have more than t common values for two different t degree polynomials. So, how to interpret this result? Again, I will not be going into the proof, but let me give you a pictorial interpretation. Let us take the case of t equal to 1 to understand this result. Okay. So, for t equal to 1, a polynomial of degree 1 is nothing but a straight line. So, the result says the following, that if you take two straight line, if you take, so this red line, this is a straight line equation. Imagine that the corresponding equation is f of x, and you have this blue line which is again a straight line. So, its corresponding equation, say it is g of x, or it will be a 1 degree polynomial. Now, it is a well known fact that if I take two different straight lines, they can have at most one point common, right, at most. It is not necessary that definitely they should have one common point. It could be the case that the two straight lines, they never intersect, they are parallel, right, or they never intersect at all. It could be the case as well, but if at all they intersect, they can intersect at most at one point, and that one point will be common in the sense it lies both on the blue straight line as well as on the red straight line. That means, I can say that this point belongs to g of x as well as f of x. Okay. So, again let us see an example to make it more clear. So, consider two polynomials f of x and g of x here, both are over this field Z7, and where the operations are addition modulo 7 and multiplication modulo 7. Now, it is easy to see that if I evaluate the f polynomial at x equal to 1, and if I evaluate the g polynomial at x equal to 1, I get the value 0. Hence, I can say that the point 1 comma 0 is common to both the polynomial f of x as well as g of x. Okay. In general, if you have two different t degree polynomials, they can have at most t common values. And how we can prove it? Actually, we can prove the second theorem using the help of the first theorem here. If you consider two different polynomials f of x and g of x, the claim is, as per the theorem, that they can have at most t common values. So, we can prove it by contradiction. So, on contrary, assume that they have t plus 1 or more common values. That means, you have say f of x 1 equal to g of x 1, you have f of x 2 equal to g of x 2, and like that you have say f of x t plus 1 equal to g of x t plus 1, where this x 1, x 2, x t plus 1 all are different. Now, if this is the case, what can I say about the polynomial f of x minus g of x? So, you consider the polynomial f of x minus g of x. Let us call this polynomial as d of x. Now, what will be the degree of d of x polynomial? Since f of x is a t degree polynomial, g of x is also a t degree polynomial, I can say that d of x is also a t degree polynomial. Okay. Now, what can I say about d of x 1? D of x 1 will be f of x 1 minus g of x 1, but f of x 1 and g of x 1 are same, hence d of x 1 is the 0 element. In the same way, d of x 2 will be the 0 element, and like that d of x t plus 1 is also the 0 element. That means, I get the conclusion that x 1, x 2 up to x of t plus 1 are roots of the polynomial d of x, but d of x has degree t, hence it can have at most t roots as per this first theorem, but I am showing you that d of x will have more than t roots, that is not possible. That means, whatever I assumed regarding f of x and g of x, that is incorrect. I assumed that f of x and g of x have t plus 1 common values, that is an incorrect assumption, hence they can have at most t common values. So, that is another interesting result regarding the number of regarding polynomials over the fields. We have two interesting properties here. So, now we will see some more properties here which will be useful for us. The last property that we require for our secret sharing scheme later is the following. If you are given d plus 1 points from f, right. So, you can imagine x 1 y 1, x 2 y 2, x sub d 1 d plus 1 and y sub d plus 1 as d plus 1 points in 2 dimension plane, okay, where it is given that the x coordinates all of them are distinct and elements from the field. That means, x 1 is not equal to x 2 is not equal to x 3 is not equal to x of d plus 1, all of them are different elements and elements from the field. Then this theorem says that there always exists a unique polynomial of degree d, call it f of x, such that this x y pairs which are given to you constitute points on that polynomial f of x or lie on the polynomial f of x. Okay. So, basically what I am saying is the following. It is a well known fact that if I give you two distinct points, okay, in the x y plane. So, this is your say x 1 comma y 1 and x 2 comma y 2, there always exists a unique straight line passing through it, that is all we are aware of. I am just generalizing that result over fields, okay, because now I am saying that this result holds even if the x y elements x y pairs are elements from the field. What I am saying is, if you are given d plus 1 such x y pairs where the x coordinates are distinct, that ensures that your d plus 1 x y pairs they are distinct elements, none of them are the same. Then you can find a unique curve, that curve I am calling it as f of x, whose degree will be d and which passes through those d plus 1 x y pairs. Okay. So, this is what I am claiming pictorially. You are given x 1 y 1, x 2 y 2, x I y I and x d plus 1 y d plus 1. Then you can always find a curve, call it f of x, whose degree will be d. That means, your f of x will be of the form sum a naught plus a 1 times x plus a 2 times x square plus a sub d x power d, where all this a naught, a 1, a 2 are elements from the field, okay, such that this f polynomial evaluated at x equal to x 1 will give you y 1, this f polynomial evaluated at x equal to x 2 gives you y 2 and so on. That is what is the claim here. Okay. Now, and the fact is that so not only there is a polynomial, that polynomial is a unique polynomial, that is also is one of the implications of this theorem. That means, you can't have two different curves f of x and g of x passing through this x y pairs, and that comes from our previous results, because in the previous two theorems we have already argued that two different d degree polynomials cannot have more than d common values. Okay. They can have at most d common values, but here we are given d plus 1 x y pairs. So, that is why there can be only one and only one polynomial of degree d passing through this d plus 1 x y pairs. So, now how do we prove this theorem? There are several ways to prove it. We will be interested basically to construct this polynomial f of x. This f of x polynomial is not given to us. We are given only the x y pairs, x 1 y 1 is given to you, x 2 y 2 is given to you, x sub d plus 1 y sub d plus 1 is given to you. Your goal is now to find out this polynomial f of x, because that is what we will require in our secret sharing protocol later. How do you get this f of x polynomial, right? So, there are several ways to do this. The most the easiest method is what we call as Lagrange interpolation. Attributed to Lagrange, who invented this method. Okay. And why it is called interpolation? Because you are basically interpolating the points x 1 y 1 x 2 y 2 and getting the unknown curve f of x. Now, it turns out that students often try to memorize the Lagrange interpolation formula, because for many of them find it slightly difficult to interpret, but there is nothing to memorize the Lagrange interpolation formula. It is a very simple formula based on a very cute idea. So, our goal is the following. Our goal is to find out this unknown f of x polynomial passing through the given d plus 1 x y pairs. So, the idea behind the Lagrange interpolation is that we should try to express this unknown f of x polynomial which we want to compute as a linear combination of d plus 1 number of d degree polynomials. Okay. So, I will be finding d plus 1 polynomials, I am calling them as delta 1 polynomial, delta 2 polynomial and delta d plus 1 polynomial. Each of them have individually degree d. We will see what will be the structure of this delta 1 polynomial, delta 2 polynomial and so on. So, the idea is that whatever is the f of x polynomial you want to compute, that can be expressed as a linear combination of these delta polynomials, where the linear combiners are your y elements which are given to you. Okay. So, remember you are given d plus 1 number of y elements. Okay. Now, these delta polynomials, they are not arbitrary polynomials, they are not arbitrary d polynomials, they are not arbitrary d degree polynomials, but they are some special type of d degree polynomials. What is the speciality of this d degree delta polynomials? So, the speciality is the following. If I consider the delta 1 x polynomial, then it has d number of roots, and what are the roots? The roots are x 2, x 3, x 4, x sub d plus 1. That means, you are given d plus 1 number of x elements. This delta 1 x polynomial has all the elements except x 1 as its root. That means, if you evaluate this delta 1 polynomial at x equal to x 2, you will get the value 0. If you evaluate this delta 1 polynomial at x equal to x 3, you will get the 0 value, and if you evaluate this delta 1 polynomial at x equal to x sub d 1, you will get 0. And if you evaluate this delta 1 polynomial at x equal to x 1, you should get the multiplicative identity element, namely 1. That is the property of this delta 1 polynomial. Okay. In the same way, if I consider the delta I polynomial, it has the property that all elements except x I are its roots. Namely, if you evaluate this delta I polynomial at x equal to x 1, you get 0. If you evaluate this delta I polynomial at x equal to x 2, you get 0, and so on. But if you evaluate this delta I polynomial at x equal to x I, you should get the multiplicative identity element. And in the same way, if you take the d plus 1th delta polynomial, it has the property that all elements, all the x elements which are given to you except x sub d plus 1 are the roots. Okay. And it is easy to see that the way the way I have defined this delta I polynomial, by definition itself each of this delta I polynomial will have the degree d. Why? Because for each delta I polynomial, so each delta I polynomial has exactly d roots, right, and hence degree d, right, because I know that a d degree polynomial can have at most d roots, but since I have defined my delta I polynomials in such a way that each of them has indeed exactly d roots, that automatically ensures that each of my delta 1 polynomial, delta 2 polynomial, delta I polynomial, delta d plus 1th polynomial, each of them has degree d. So, now my claim is that this unknown f of x polynomial is nothing but this linear combination, namely y 1 times delta 1 x polynomial, y 2 times delta x polynomial, and so on. So, why f of x will have degree d? Because each of these delta polynomials, they have degree d's, and now if I multiply a polynomial with some constant, y 1 is a constant. So, overall this is a degree d polynomial. Similarly, y 2 times delta 2 x, that will be a degree d polynomial, and in the same way y I times delta I x polynomials, that will be a degree d polynomial, and this last linear combination, it will be a degree d polynomial. And now if I sum up several d degree polynomials, I will again get a degree d polynomial. So, it is given guaranteed that whatever f of x I compute by computing this linear combination, that will be a degree d polynomial. And now, do I get the guarantees that I have in the theorem? What can I say about f of x 1? So, if I evaluate f of x 1, then that will be same as y 1 times delta 1 polynomial evaluated at x 1, but delta 1 polynomial evaluated at x 1 give me 1 plus y 2 times delta 2 polynomial evaluated at x 1, but delta 2 polynomial has the property that x 1 constitutes its root. So, delta 2 polynomial evaluated at x 1 will give me overall 0. That means, all the remaining terms here will give me 0 and 0 added with a non-zero element will give this non-zero element, and y 1 multiplied with y 1 will give me y 1, right. In the same way, f of x I will be y 1 times delta 1 polynomial evaluated at x I, but x I is one of the roots of delta 1 polynomial. So, I will get y 1 times 0 plus y 2 times 0, because delta 2 polynomial evaluated at x I will give me 0, and like that it is only the ith term in this f of x, which is y 2 times delta I polynomial evaluated at x I will survive, and remaining everything will become 0. So, this becomes 0, this becomes 0, last term becomes 0, it is only the ith term which will survive. So, sorry, this should be y I, and delta I polynomial has the property that x I does not constitute its root. When it is evaluated at x I, it gives me 1. So, y I into del 1 will give me y I. So, indeed this f of x has all the properties. It has degree d, and indeed when evaluated at x 1 it gives me y 1, when evaluated at x 2 it gives me y 2, and so on. Now, if you want to see the structure of the delta I x polynomial, this will be the structure of your delta I x polynomial. So, all the elements you can see in the numerator, I have the terms of the form x minus x 1, x minus x 2, x minus x of I minus 1. So, basically the term x minus x I is missing in the numerator. Why it is missing? Because I do not want x of I to be the root of this polynomial, remaining all elements should be the root. So, x 1 should be root, x 2 should be root, x of I minus 1 should be root, x of I plus 1 should be root, and so on. So, that is why in the numerator I have d terms like this, and in the denominator I have terms like x I minus x 1, x I minus x 2, x I minus. So, now you can see indeed if I substitute delta x equal to x 1 say, then because since I have in the numerator x minus x 1, if I substitute x equal to x 1, I get 0 in the numerator, and hence overall it becomes 0, right. So, that like that you substitute any value of x except x I, this delta I polynomial will vanish, it will become 0. Whereas, if you substitute x capital X equal to x I, then both your numerator and denominator will become same, and hence it will take the value 1, right. So, there is nothing to memorize here, you just need to ensure, just remember this property that delta I x has the property that all the elements except the ith x element should be root, and that is possible if you write all these product terms in the numerator. And to ensure that this delta I polynomial takes the value 1 at x equal to x I, you write down the corresponding differences in the denominator, as simple as that, right. So, this is your Lagrange interpolation, and this is the general form of your delta I x polynomial. So, now if you are wondering that this in the denominator, whatever is there in the denominator, I am dividing the numerator by the denominator, that is not the case. Remember, all the operations are the field operation, and the field operation we do not have what we call as division. Division should be interpreted as if I am multiplying the numerator with the multiplicative inverse of the denominator, right. So, let me call this entire denominator as C sub I, okay, and it will be a non-zero value, non-zero element from the field. Why? Because of the fact that none of the given x values are same, all of them are distinct. So, if I take differences, pairwise differences, I will get a non-zero element, and since C I is a non-zero element, this delta I polynomial should be interpreted as if I am dividing by 1 over C I, but 1 and remaining whatever in the numerator, but 1 over C I should be interpreted as if I am multiplying the numerator by the multiplicative inverse of my denominator. And since C I is non-zero, remember one of the properties of the field is that all the non-zero elements are guaranteed to have its multiplicative inverse. So, multiplicative inverse here is possible. Right. Another interesting property of Lagrange interpolation which we will require later is the following. Imagine you are given d plus 1 x y pairs where the x coordinates are distinct. We know as per the Lagrange interpolation that we can compute a curve f of x passing through this x y pairs. And now imagine you are given a new x value, say you are given a new x coordinate x sub nu, which is different from all the given previous x coordinates, and you want to compute the value of this f of x curve at x equal to nu, right. That means, you want to find out that what should be the corresponding y value. Now, since my f of x curve is this as per the Lagrange interpolation, the value of f of x nu can be computed as follows. I just substitute x equal to x nu in the Lagrange interpolation formula, and then I get the value of the f curve at x equal to x nu. Okay. Right. Now, let us see some more interesting properties of t degree polynomials over field. So, let me call this set P superscript s comma t to be the set of all t degree polynomials over the field whose constant term or constant coefficient is the element s, right. So, each such polynomial, each polynomial from this collection P superscript s comma t will be a polynomial which will have t plus 1 coefficients. It will have the coefficient a naught, it will have the coefficient a 1, it will have the coefficient a t. But since I want the constant term to be the constant term to be the value s, I do not have a choice for a naught. My a naught has to be compulsorily s. Remaining other t coefficients can be any element from the field. Okay. So, that is why it follows that the number of polynomials f of x which are elements of this bigger set of polynomials whose constant term is the element s, the number of such polynomials is the number of elements that you can have in the field raised to the power t. Why so? Because a 1 can take any of these many values, right. So, if say for instance the cardinality of f is 10, if there are 10 elements in your field, okay, or say 7 elements in your field, then a 1 could be any of those 7 elements. A 2 also can be any of those 7 elements and so on. So, that is why how many possible polynomials I can have? I can have these many options for the first coefficient, I have these many options for the coefficients for x square, I have these many options for the coefficients for x cube, and like that I have these many options for the coefficient of x power t. Okay. So, this is basically the number of elements in the field raised to the power t. These many possible polynomials you can have. Okay. Right. So, let us see an example here. Imagine my t is equal to 2, my field is Z3, Z3 means my elements could be 0, 1 and 2, and my plus operation here is addition modulo 3 and my multiplication operation here is multiplication modulo 3, and imagine my s is equal to 1. So, now if I want to list down all possible polynomials of degree 2, where the coefficients could be either 0, 1 or 2, okay, and whose constant term is 1, then that collection of polynomials as per my notation is this, and you can see that now I have how many 9 f square number of polynomials, and f cardinality is basically here 3 because I have 3 elements in my field. So, 3 square which is 9 possible polynomials. So, you can see this is a polynomial of degree 2. You might be wondering that there is no term like x and x square, but that is fine. I can always imagine that I have a term like 0 x and 0 times x square. So, overall this will be treated as a polynomial of degree 2 whose constant term is 1. This is a polynomial of degree 2 whose constant term is 1, another polynomial. So, all the polynomials have their constant term as 1 and the maximum degree could be 2 and number of such polynomials is 9, right. Now, another property which we can derive based on whatever we have discussed till now is the following. Imagine you are given t pairs, t x y pairs. Pictorially you are given t number of distinct points in the x y coordinate, where this all x and y elements are elements of the field, and these x coordinates are different, which ensures that these points are distinct points. Now, if I take an element s from the field, okay, that is element s could be any element from the field. My question is, how many possible polynomials can be there whose constant term is s and where this x y pairs also constitute the points on that polynomial. Basically, how many polynomials from this set. So, this is the bigger set, this is the set of all possible t degree polynomials whose constant term can be s. I am asking that from this collection, right, namely from f power t number of polynomials, how many possible polynomials can be there whose constant term is s, namely the point 0 comma s lies on that polynomial, as well as the remaining t distinct points which are given to you also lie on that polynomial. And it turns out that there is only one possible polynomial from this set. You cannot have more than one polynomial from this set satisfying this property. This is because you are already given t number of pairs, x y pairs, t number of points, and you also want that 0 comma s should also lie on that polynomial. So, overall you have now t plus 1 points, and through t plus 1 points you can have only one polynomial of degree t passing through all t of t plus 1 of them. You cannot have multiple, you cannot have a polynomial f of x belonging to this set p of s comma t as well as g of x also belonging to p of s comma t, such that your f of x 1 x I 1 is equal to y I 1 and g of x I 1 is also y I 1, and like that f of x sub I t is equal to y sub I t and g of x sub I t is equal to y sub I t. That is not possible, because that means anyhow, since both f of x polynomial and g of x polynomial has their constant term as s, you also have the condition that f of 0 equal to s, g of 0 is equal to s, and hence you get that f and g polynomials, even though they are different polynomials of degree t, but they have t plus 1 common values. That is not possible. So, that means there can be only one f of x polynomial whose constant term is s and whose degree is t, and which can pass through these given t distinct points. You cannot have another g of x polynomial possible, right. Fine. So, now let us see another important property of t degree polynomial. So, this property, for demonstrating, I will consider a random experiment here. So, in this experiment, I call this experiment as experiment Shamir. attributed to Adi Shami, who gave this experiment. So, what is this experiment? So, the input to this experiment is some element S from the field F. Now, the experiment does the following: it randomly picks a t degree polynomial, call it f of x, whose constant term is S, right. So, this notation belongs to and in subscript r, that means this picked randomly, uniformly at random. Remember, there are many possible t degree polynomials whose constant term could be S. I am just randomly picking one of them. And the output of this experiment is the value of this randomly chosen polynomial at n publicly known distinct values. So, the outputs are f of x 1, f of x 2, f of x I, f of x n, all of which are elements from the field. None of them is 0 and all of them are distinct. So, let me call the value of f of x I as y I. So, your outputs are y 1, y 2, y sub n, a very simple experiment. So, now you can see that if I run this experiment different times, my output could be different. First time I run this experiment with the input S, the polynomial f of x that I might choose might be different from the polynomial which I pick when I run the same experiment with the input S, because every time I am picking the polynomial randomly, I am not fixing the polynomial f of x, that is important. Okay. That is why this is a probabilistic experiment. Right. That means, even though the x values x 1, x 2, x t, x n, they will be fixed, for each instance of the experiment, fixed. Since my polynomial f of x is randomly chosen, my outputs y 1, y 2, y t, y n can take different values with different probability. Okay. Now, I want to measure the following. Given this experiment where the input S is not known to you, I will not be telling you the input S. How much information about this input S is learnt if I just give you any set of t output values. So, I will not give you the full set of n output values, but I just give you any set of t output values which I obtain by running this experiment. It is like saying the following: I am a kind of a person, I want to challenge you. I run this experiment with some input S which is known only to me, and I generate the n outputs, and I give you any t of the n outputs that I have generated, and I challenge you what was my input S, how much information about the input S you learned. Okay. So, let us assume for simplicity that I give you the first t output values, but whatever I am discussing here, it holds even if I give you t output values which are not the consecutive t y output values, right. So, I may give you say y 1 and then I do not give you y 2, but I give you y 3, and then I do not give you y 4 and I give you y 5 and y 6 and so on. But overall I give you t number of y output values, x output values are anyhow known to you. I challenge you how much information about S you learn. The thing is, from your viewpoint, you do not know what was the curve f of x that I have chosen. You only know that in the experiment I have chosen the curve f of x uniformly at random, but that f of x curve could be such that its constant term could be say an element S 1 from the field, or it could be also the case that the curve that I have chosen was such that its constant term was S 2, that means my input in the experiment was S 2 and the polynomial that I evaluated when evaluated at x 1, x 2, x t gives you the values y, gives the output y 1 to y t, or it could be the case that my input in the experiment was say the third element from the field, because I have chosen a t degree polynomial whose constant term was the third element from the field and so on. So, just based on the knowledge of t output values that I give you from this experiment, you cannot pinpoint what was the curve that I had chosen, and hence from your viewpoint it could be any element from the field which was my input in the experiment. More formally, what we can prove here is the following. You take any y1, y2 up to yt from f. The probability that the y1 to yt that I am giving to you and which are elements from the field, they are generated as an outcome of the experiment where a polynomial f of x was chosen whose constant term was s, is the same as the probability that the same y1 to y2, y1 to yt would have been generated if in the experiment I would have chosen a polynomial g of x whose constant term would have been s prime. That means, I am now going to show you it does not matter whether my input is s or whether my input in the experiment is s prime. If I just focus on any subset of t output values generated in the experiment, with equal probability those t output values could have been generated from the input s or could have been generated from the input s prime. You cannot pinpoint just based on the t output y values whether you are seeing the output corresponding to the experiment run with input s or you are seeing the output for an experiment which was executed with the input s prime. So, let us formally prove this. So, let us consider the first probability here. I want to compute the following. What is the probability that in the experiment the f of x polynomial is chosen randomly from this set? That means, basically I am asking here experiments input was s, because if the polynomial is chosen from this set, that means the input was s, and given this you see the first t outcomes to be y1 to yt. That means, that randomly chosen polynomial evaluated at x1, x2, xt gives you the values y1 to yt. My claim is that this probability is 1 over the cardinality of the number of t degree polynomials whose constant term is s. This is because y1 to yt, x1 y1 up to xt yt, they are t points, and now if you add 0 comma s also, you basically get one more point. Through this t plus 1 points, there can be only one t degree polynomial, call it f prime of x, passing through all t plus 1 of them. There cannot be multiple polynomials whose constant term could be s and satisfying or lying passing through x1, y1, x2, y2, xt, yt and so on. There can be only one t degree polynomial, but I am choosing the polynomial f of x randomly, right. So, my sample space here is the set of all possible t degree polynomials whose constant term could be s. So, that is the cardinality of the sample space, but out of these many number of t degree polynomials whose constant term could be s, there could be only one t degree polynomial which satisfies the condition that f of x1 is y1, f of x2 is y2, f of xt is yt. That means, this condition will be true only if the f of x polynomial which I am randomly choosing here is actually f prime of x. But since f of x is randomly chosen, the probability that f of x is equal to f prime of x becomes overall this. In the same way, the second probability expression here tries to capture the following. Your experiment's input is s prime, because you are picking now the polynomials from the set of polynomials whose constant term is s prime, where s prime is different from s. But still you want to measure the probability of the event that a randomly chosen t degree polynomial whose constant term is s prime when evaluated at x 1 gives you y 1, evaluated at x 2 gives you y 2, evaluated at x t gives you y t. Again because of the same reasoning that we have given just now, the probability of this event is also the same whatever was the probability of the above event. That means, what we have formally proved here is that in this experiment if I just give you any subset of t output values, I do not give you the full vector of n output values, I run the experiment with some private input, but I give you only a partial subset of the output, namely I just give you tell me which t output values you want, I will give you those t output values. My claim is from your viewpoint those t output values could have been generated with equal probability both for input s as well as input s prime, and hence you does not learn any information about my input for the experiment. Okay. So, let us make this property, let me demonstrate this property with this example where I take the field to be Z17 and my secret not my secret, my input in the experiment is 13 and I am fixing my evaluation points to be 1, 2, 3, 4, 5. Okay. That means, suppose in the experiment here my input was 13, I could have chosen any 2 degree polynomial whose constant term is 13, I am picking them randomly. So, imagine that I pick this polynomial, this is my polynomial which I have chosen, but I am not telling you this, I am running this experiment myself. And if I evaluate this polynomial at 1, 2, 3, 4, 5, I get these y values. Now, you come to me and ask for any 2 of the 5 y values. Suppose I give you the first 2 y values, not the first 2, say you ask for say the first and the third y value. So, I give you y 1 equal to 8 and y 3 equal to 10. And now, I ask you, can you tell me what was my input? Was it 1, was it 2, was it 0, was it 5? Which element from Z17 I have used as my input in the experiment? And now, you can see what I am doing here is, you can do the following. You can ask yourself in the mind, is it the case that my input in the experiment was 0 and you got outputs y 1 equal to 8 and y 3 equal to 10? Well, that is quite possible if in the experiment I would have chosen this 2 degree polynomial, because indeed this 2 degree polynomial has its constant term 0 and when evaluated at x equal to 1 gives you 8 and when evaluated at x equal to 3 gives you 10. Or if you ask in your mind that is it the case that my input was 1 in the experiment, well that is quite possible if in the experiment I would have chosen this 2 degree polynomial and indeed this 2 degree polynomial when evaluated at x 1 equal to 1 gives you 8 and when evaluated at x 3 equal to 3 gives you 10. And now, like that if you analyze in your mind that whether this output y 1 equal to 8 and y 3 equal to 10 can come from different candidate s values, each of the candidate s value is equiprobable from your viewpoint. You cannot pinpoint what was my input in the experiment, it could have been any input from the field Z17 which would have given you the output y 1 equal to 8 and y 3 equal to 10, and hence each possible input is equiprobable. Okay. So, with that I end today's lecture. Thank you.